Okay, so this is our circuit. It's an RL circuit. And a while ago, from the first sample problem, we have determined the equation. And this is our equation already. This equation is still usable, can still be applied in this case because this is a source-free circuit, doesn't have any electrical potential here. Okay, so if we add up all the voltage drops, it will be equated to 0 for this circuit. So we have this, and it says that our initial current is 2 amperes. So you see there's the 2, and it was given, you could see in the figure that your resistance is 200 ohms, so it was substituted, and your inductance in henries is 50 millihenries. So that would be divided by 1000. So there's a need for us to divide this by 1000. That then would be 0.05. This is the This would be our equation plus for this particular circuit. So at time greater than 0, this would be the transient response of our circuit. Or this would be the current that is flowing through our circuit elements at time greater than 0. If we intend to determine the value of the current at a particular time of 200 microseconds, what you're going to do is substitute 200 times 10 raised to negative 6 here for the time because it's in microseconds. So times 200 times 10 raised to negative 6. The value that you'll be computing for the current is 0.8987 amperes, or that would be 898.7 milliamperes. So that's a case of a substitution, or we're making use of the formula that we got in number 1 here in this particular circuit and made use of it in the second circuit because, again, we don't have an electrical potential written here. So it's a 0. So that would be our current. Now we'll look for a different application of the RL circuit wherein we're going to set up the DE starting from the equation that I gave you as a guide. This one. The equation wherein your unknown function is current and your independent variable is time. And that problem would be this. Okay, an RL circuit has an EMF of 5 volts. So take note, it's now having an EMF of 5 volts. So this is DC. A resistance of 50 ohms, and an inductance of 1 Henry. And there's no initial current. Find the current in the circuit at any time t. So this particular problem now will help you derive another general formula wherein this time you have already an EMF of 5 volts, or you have a value that is constant for the EMF, and this time there is no current that is flowing in your circuit. So it was identified here that E is 5, R is 50, and L is 1. If we go back to our DE, the DE that I've shown to you a while ago for the RL circuit, this one, di dt plus R over L times I is equal to E over L. So that's the same DE we're going to use here. Okay, so you have di dt plus, you have 50 divided by 1. So that would be 50 for the R divided by L. Then we multiply it with the I. Is equal to the E, which is 5, divided by, again, by L, which is 1. So this is our DE. Again, this could be solved using separation of variables or linear differential equation. If we treat it for, let's say, for a case of, we will have a different approach to this DE. If we treat it as a linear DE, your integrating factor will be e raised to negative 50t. Since we're done already with linear differential equations, the equation that you will be having is I equal to C e raised to negative 50t plus 1 over 10. How did this particular equation came about? You find the unknown function I, Yeah, that should be multiplied to the integrating factor e raised to 50t in here on the left side is equal to the integral of this, the 5 times e raised to 50t. Because that's how we do it. If it's 50t, you need 50 as its derivative and you divide by 50. So the 5 divided by 50, that would be your 1 over 10. The reason why you have an e raised to negative 50t here, it's because the e that you have here on the left side was already used as a divisor for the entire equation. And then it's left, the left side now is left with just the I being equal to c e raised to negative 50t. This is your constant of integration plus 1 over t. The e raised to 50t here was already cancelled by the division of e raised to negative 50. This is your general dE, but still your constant of integration is unknown. If you substitute the condition that there's no current flowing in the circuit at time 0, then t at t0, I is 0. If you substitute it here, this is 0, this is 0, this would be c. Then your c will be negative 1 over 10. Because e raised to 0 is 1, so this would be a c. Your current I here is 0. So 0 is equal to c plus 1 over 10. If you transfer the 1 over 10 on the left side, that would give you a c, which is negative 1 over 10. Now, if you're going to write now a more general equation, now without the arbitrary constant of integration, from this one, then you just substitute the negative 1 over 10 for the c. So now your I will be negative 1 over 10 e raised to negative 50t plus 1 over 10. What we did here is simply find the c. That way, given that time for my RL circuit, I will be able to know the current. What is that particular current depends on how the problem asks for it. So I have written something here below. The quantity, this quantity class O, which is negative 1 over 10 e raised to negative 50t in the current I is called the transient current. Why is it called the transient current? It's because after a very long time, that is when you substitute t approaching infinity here, this entire term will be equal to 0, or its value goes out to 0. We call that the transient current. Or shall we say, for this RL circuit, your transient current is represented by negative 1 over 10 e raised to negative 50t. And actually, the value of this will be equal to 0, this entire thing. Why? Because this is e raised to negative infinity. That would be 0. If you multiply it to negative 1 over 10, that will still be a 0. This is called your transient current. This is the explanation. The quantity 1 over 10 is called the steady state current. Why? Take note, the steady state current. Why? Because after a very long time, if this term, your transient current, has a value equal to 0, this constant is the only thing left to be accounted for in this equation. After a very long time, then, your circuit will have a current of 1 over 10 amperes. This is your steady state current. This is your transient current. So let's say, for example, you would be asked, given the solution of a differential equation for an RL circuit that was asked for you to be set up, and you would be asked what is the transient current. You copy the entire term that has the exponential expression, or you copy the entire term which has the t. If you substitute the t for such an expression and the value of that entire term goes to 0 as stated here, then this is your transient current. It's so easy to answer the steady state current because whatever is the constant in that equation you have derived, that is your steady state current. Wala na kada tan-awon ni iban basta may constant ka makita sa gin-derive mo nga formula that is already your steady state current. Why? Because that's the only thing that is left when all the other terms are having values equal to zero. But in the case of the RL circuit class, we will only have two terms anyhow. The term that is representing the transient current and the other term which is representing the steady state current. So the steady state current has a value that is not equal to zero when t approaches infinity. The transient current has a value which is always equal to zero when t approaches infinity. Okay? So now you're learning what a transient current and what's a steady state current in the case of this RL circuit, which is not now source free. So we have now a 5-volt source. So I like to end with this RC circuit application. Anyway, this would be more or less the deviation in the type of problems that you will be encountering later on in terms of the application of DE for circuit problems. This time we have an RC circuit with an EMF of 400 cosine 2t. I chose this particular sample problem because this time your source is an AC source. You have an AC circuit because your E is not anymore constant. That is a function of time. So your resistance for these circuits is 100 ohms and the capacitance is 0.01 farad or 10 raised to negative 2 farad. Initially, there is no charge on the capacitor, meaning Q is 0 at time equal to 0. Find the current in the circuit at any time t. Now, what do? We find the current in the circuit at any time t. We cannot determine the current initially here, class, but we need to go back to the standard DE that we can use for an RC circuit. And that DE is this, the one that I have shown you here on top, the standard DE for an RC circuit. A known function is Q, the charge, independent variable is time, and we have the current as equal to dq dt. So meaning this entire derivative class in here is actually the current flowing through our RC circuit. So we have Q over RC for the second term, and we have E over R on the term on the right side of this DE. This is the same DE that we started off in this second sample problem. So your 1 over RC, you have 100 for the R, and your C is 10 raised to negative 2. If you multiply these two, the answer is 1. So that's the reason why you have only a Q. This is supposed to be Q over RC. Now this one is E. If this should be 400 cosine 2t over R, which is 100. So then that leaves us with 4 cosine 2t. Now, this particular equation that you have here is linear. This cannot anymore be solved using separation of variables because you already have the Q here and you have the time here. So you have to apply what you've learned in linear differential equation. You need to determine the integrating factor. It's easy in this case here because your constant, in here your P of t, because this one is your Q of t, your P of t here is just 1. So if you take the e raised to P of t dt, your integrating factor will be e raised to negative t. This is e raised to negative t. This one, this is your Q of t. But when you process a linear DE, this Q of t will be multiplied to your integrating factor e raised to negative, rather e raised to t in this case, because this time we have already divided here. So that is why it became negative. So you will have, as it says here, a solution which will be requiring two integration by parts. So I want you to as an assignment to review how you integrate an exponential function together with a trigonometric function. This is what they say then in our language nga may balik-balik ka ma-equate ka da sunsulbon mo ang DE nga E raised to something, E times something. So this is what it meant here. But nonetheless, class, if you do the mathematics, the answer for the Q will be this one. So that would be your assignment later on. You do your homework and check whether if you really do integration by parts correctly, the final Q expression with the constant of integration C would really be this. Just like what we did in number 3, you equate Q equal to 0 at time equal to 0 in order to find the C. And this is your C now. So your C is equal to negative 4 over 5 in here from this particular equation. Knowing this, you go back here and substitute. This one allows you to determine the charge in your capacitor at any particular time. So you just substitute time in seconds here. And by the way, class, before I forget, whenever you substitute time in the sine and cosine function, in cases wherein your E is in terms of the time variable, your calculators should be in radian mode. It should be in radian mode because the value of time that you are substituting is a radian value. It's not a degree value. Then you'll be able to determine the Q, the charge in coulombs. So find the Q and then obtain the current. So now you have find the Q. How do you find the current? You go back to this. You have already Q, but that Q is equal to, where is that? Q is equal to, I is equal to dq dt. In order for you to find the current, what will you do? Because what you have here is Q. This one. How will you find the current? What you have here is Q. What you do? What will you do? It's dq dt. Current is equal to dq dt. What will you do? If I will ask, I'll just borrow probably 2 to 3 minutes of your time. What you have here is an equation of Q. But the problem is asking what is the current. So you're asked for the charge. This is your answer already. But then obtain the current. How will you obtain the current? What will you do? Let's see.
Differentiate means.
Very good, very good. You differentiate this because current is equal to dq dt. You will differentiate this in terms of time. You know how to differentiate this one. It's simple. Sine, cosine, you differentiate this. And that would be now I equal to dq dt and the corresponding derivative of this. So given the time, you can also solve for the current in amperes in your circuit. So take note, class, even if you're given an RC circuit and you are asked for the time, start always with the fundamental DE in terms of the charge. Because the answer that you will be getting later on for the charge will lead you to the current. Because all you need to do is differentiate. Okay? That's it. So I will be posting your problem set for Wednesday later on, or probably early part of tomorrow morning, because I have deadlines to meet tonight. And you will not see each other on Wednesday, but you will have your quiz on Friday. Feel free to message me if you have any questions regarding the problems, or if you intend to have guidance on how to find your way through the problems. Okay, class? Thank you for being patient. I used up 3 minutes of your time. I will update you on our schedules, especially for those who just came in late in our campus and in our GC. Thank you.
Thank you, Miss.
Thank you.
Thank you and goodbye, Miss.
Goodbye. Bye.